So we have set up the reliability problem as the crossing of a safety margin m from the positive domain to the negative domain. And the very first time that happens, we have the time to failure. So let us see if we can find out the rate at which this crossing happens, first for a general stochastic process, and then what form it would take if the process is stationary, and particularly stationary Gaussian. So let's say we first define the rate of crossing of a certain barrier A by the process x of t, and let's say from below. So that's how you see the plus in the superscript of the rate, and the subscript A specifies the barrier which the process is crossing. So the probability that exactly one crossing like this would occur in small time interval dt by the process would be the rate times the length of that small interval. So we could write this in terms of the process itself, that at t it is less than a, and at t plus dt it is at a or above. So that we can now expand in terms of the derivative process up to the first order approximation, that xt is less than a, and xt plus x dot t dt is greater than or equal to a. And we could do some rearranging, and we emphasize the fact that x dot t is non-negative because, and that is consistent with our assumption that we are talking about up crossing. So we are talking about crossing the barrier from below. And then after some rearrangement, we could express the same probability as that in which xt is less than a and greater than or equal to a minus x dot t dt. So now we have a probability involving a random variable x and another random variable x dot. X dot t is the derivative process. So at that particular instant t, we find that this is the joint probability integration of x and x dot over the regions that x dot takes all possible positive values, and x is limited between a minus x dot dt and a. So because the interval is so small, we can convert this double integration into a single integration, one-dimensional integration on x dot, and roughly replacing the contribution of x as the size of the interval. So it's a minus x dot t to a. So we are left with the interval which is x dot dt. So nu a plus dt, that is equal to dt times a one-dimensional integral with respect to x dot. So that lets us cancel the dt on both sides and express the rate of upcrossing of the barrier A by the process x as an integration of x dot and the joint density function of x and x dot, x being fixed at A, in terms of all possible values of the x dot. So now let us see what form this would take if we specify that the process x is Gaussian, and not only that, stationary Gaussian. And soon we are going to say that let it also be zero mean Gaussian. So it's a known result that if xt is a Gaussian process, then x dot t is also Gaussian, and if xt is stationary Gaussian, then x dot t is zero mean stationary Gaussian. And not only that, xt and x dot t are independent at the same instant. So that's actually a very useful property, because you can guess that the joint density function that we had in the left side of this screen, we can now write this as the product of the two marginal densities. And as I said, let xt be zero mean as well. It's going to help us. So in that case, the rate of upcrossing of the barrier A becomes, and now we are going to bring in the Gaussian nature of x and x dot, and because they are independent, you see the well-known form of in the exponent minus a square over 2 sigma square for the first variable, and minus x dot square over 2 sigma x dot square for the second variable. And there's of course no correlation term because they're independent. And then this simply becomes an exercise in integration, and we can compute this using known results. So the integration of x to the power m exponential minus 3x squared dx, we know that it depends on the gamma function, and when m is equal to 1, it takes the very simple form gamma 1 divided by 2 over 1 by 2 sigma x dot square. So this basically simplifies to the density function of one Gaussian random variable evaluated at A, and then multiplied by the ratio of the standard deviation of the derivative process and the parent process. So that gives us the rate of crossing of our barrier A by the stationary Gaussian process x, the stationary zero mean Gaussian process x of t. Now, if now we specify that the barrier A is 0, and you can guess why we are doing that, because we defined failure as the crossing of the barrier 0 by the safety margin. So naturally, if we put A equals 0, so then the rate of upcrossing of the barrier 0 is 1 over 2 pi times the ratio of the standard deviations, and by symmetry, the downcrossing rate would also be the same. So we can nicely express these rates in terms of simply the ratio of the standard deviations of the two processes, of the process and its derivative process. So then we are able to express the reliability problem now in terms of an appropriately defined safety margin, which we have used the generic term x. So if we have a safety margin process which is zero mean and stationary Gaussian, then we already know what this would look like. So now there is also a very useful result that for a stationary process, this sort of crossing, if we see repeatedly the times at which the process makes such crossings, it becomes asymptotically a Poisson process. So we know that a Poisson process is defined only by its rate, and the rate is simply these rates that we have computed. So it's nu 0 plus or nu 0 minus, and that tells us that if we are interested in the very first time that such a crossing occurs, we are talking about an exponential random variable. So this reliability then simply becomes exponential of negative of the downcrossing rate times the interval length t. So that would be the reliability function, and the time to failure is an exponential random variable with rate nu 0 minus. Now, more generally speaking, if the process starts from the unsafe set, so obviously there is no crossing involved. So we for the sake of completeness, we would want to know the probability that it starts from the safe set, and we've called that R0. Then obviously we need to multiply this exponential minus nu 0 minus t with the quantity R0. But in general, R0 is 1, so we will not need to worry about that.